You know that new car smell? How about that new car shine? Or a brand new phone screen just perfect? But it never lasts, does it? Well, today we're going to find out why. We're going deep, I mean microscopic deep, to hunt down the tiny villain responsible for all of it, the microcrack. Let's do this. Right? I mean, it's that feeling, isn't it? You get something brand spanking new, a phone, a car, whatever, and it's flawless. But then, time happens. The shine starts to fade, little marks show up out of nowhere, and it turns out the whole process, this slow decay, it all kicks off with damage so tiny you literally can't see it with a naked eye. Okay, so here's how we're going to break this down. First, we're going to shine a light on these invisible cracks. Then we'll look at how they're a double whammy, wrecking both a product's looks and its strength. After that, we'll play detective and trace a single crack all the way back to its birth. We'll check out the cool tech scientists use to hunt for them, and then wrap up by looking at how we can build better, tougher stuff in the future. All right, first stop, the microscopic crime scene. You see, the real culprits behind all this wear and tear are these super tiny flaws. And get this, they're in the very coatings that are supposed to be protecting our stuff. Yeah, you can think of these coatings kind of like a thin layer of armor. They're on everything from your glasses to jet engines. The problem is, this armor, it's not always perfect. When you put it under stress, it can develop these tiny, tiny fractures. And that's where all the trouble begins. And that brings us to culprit number one, the microcrack. Now, the definition makes it sound simple, right? A microscopic fracture. But don't let that tiny size fool you. This right here is ground zero. It's the starting point for pretty much everything that goes wrong. And once you have a microcrack, it opens the door for its partner in crime, delamination. This is a fancy word for when the coating just gives up. It starts to lose its grip and peel away from the surface it's supposed to be protecting. So if the coating is armor, delamination is that armor literally falling off. Not good. Okay, so now we see how this tiny little crack starts to become a really big problem. Because these flaws, they don't just do one type of damage. Oh no. They wage a war on two separate fronts. They go after a product's looks, its beauty, and its actual strength, its brawn. And it really is a two-front war. On one side, you've got the visual impact, just the way it looks, the aesthetics. But on the other side, you've got the functional impact, the way it actually works, its durability. And a single tiny crack is all it takes to mess up both. It's wild. So let's talk about the aesthetic damage first, the beauty part. These microcracks, they create these rough little patches that mess with how light bounces off the surface. That's why something that was once super glossy can suddenly look dull and matte. They cause uneven color, they trap dirt, they lead to pitting and discoloration. Yeah, long story short, they are literally the reason new things stop looking new. But honestly, the functional damage, that's where things get really serious. A crack actually reduces the amount of surface that can take a load, which weakens the whole thing. It messes up the glue, the adhesion, holding that protective coating on. And maybe worst of all, it creates these tiny little highways for nasty stuff like water and salt to sneak in and cause corrosion underneath. It's a total disaster waiting to happen. So, okay, we get what these cracks do, but where do they even come from? Like, how is a crack actually born? Well, to figure that out, scientists basically have to torture these materials in the lab. They put them under some pretty extreme stress. And what they've mapped out is basically the anatomy of a failure. It all starts when some kind of stress is introduced. In the lab, maybe it's a tiny, sharp point pressing down. The very first sign of trouble is this event that scientists call a pop-in. You can think of it like a microscopic dent. It's the first moment the material gives in. That little flaw then weakens the bond between the coating and the surface, and boom, that's all the invitation delamination needs to get started. But, it's not always about a direct hit. Cracks can be born for other reasons too. For instance, if the coating and the material it's on expand and contract at different rates with temperature changes, that can cause a crack. Or maybe there's stress left over from the day it was made. Even just chemical breakdown over time can do it. And here's the thing, no matter how a crack gets there, the impact is totally measurable and totally direct. This quote from the research really nails it. The more cracks you have and the bigger they are, the more you see a drop in all the important stuff, like hardness and toughness. So the science is crystal clear. More cracks equals a weaker material. Period. So that raises a pretty big question, right? How on earth do you study something you can't even see? Well, this is where things get really, really cool. Scientists have this amazing high-tech toolkit for hunting down these invisible flaws.
Let's peek inside that toolkit, shall we? First up, you've got the Scanning Electron Microscope, or SEM. This thing is like a superpowered magnifying glass that can literally map out every single crack on a surface. But if you want to get even closer, you use an atomic force microscope, the AFM. It can actually feel the shape of the surface, down to the level of individual atoms. And finally, they get physical. They use scratch and fatigue tests, which is basically a fancy way of saying they beat up the material to see exactly when and how it breaks.
Okay, so understanding the problem is one thing, seeing the damage is another, but the big question is, what do we do about it? How do we fix this? So for our final section, let's look at how scientists are fighting back and trying to build the flawless surfaces of the future. And the real game changer here is a shift in thinking. We're moving from being reactive, fixing things after they break, to being proactive. The goal isn't just to repair damage anymore. The real goal is to design coatings that don't even let cracks form to begin with. So how are they doing that? Well, with some pretty brilliant strategies. For example, they're designing coatings that can actually stop a crack in its tracks, kind of like ripstop fabric for your jacket. Other designs are all about spreading out stress evenly so it doesn't build up in one weak spot. They're also building coatings in these super complex layers. Think of it like microscopic plywood, or even mixing in nanoparticles to make the whole thing tougher from the inside out. And what's really amazing is when they start combining these strategies. For instance, imagine using a super high precision laser to treat a surface before you even apply one of those advanced multi-layer coatings. When you put those two things together, you get a surface that is unbelievably uniform and just incredibly tough against the exact kinds of stress that would normally make it fail. So all this incredible research leaves us with one last big question. With all these advancements, could we actually one day design a perfectly flawless surface? A world with no more wear and tear? I mean, it sounds a little like science fiction, doesn't it? But it is the very real, very serious goal that's driving the next generation of material science. Pretty amazing to think about.